Now, moving on to the next topic, we have here halides. Okay, so in halides, I want to see the order of electron density. So, halides, we know that fluorine, all the halides have lone pair of electron. So, taking the example of fluorine here we have fluorine, and thus the electron pair will start to delocalize themselves here, and you know what happens is the bond starts moving and everything. So since fluorine is electron rich and has a lone pair, it will show plus M effect. So lone pair present, we know when lone pair is present, plus M effect is shown. That part we are aware of. The next one, of course, chlorine also now has a lone pair of electron because all of them are halogens, bromine also, and so does iodine. So all of them have lone pair of electron, and thus all of them will show plus M effect. Bromine 2 and iodine 2. But we should know this, that apart from fluorine, chlorine, bromine, as well as iodine have vacant orbitals. So they have vacant orbitals, and we know that if there is presence of vacant orbitals, then they are bound to show minus M effect. So moving on, we know that now chlorine has a minus M effect, bromine 2 has a minus M effect, and iodine 2 has a minus M effect. Therefore, the plus M effect here is shown by only fluorine, and the rest of them will have plus M as well as minus M effect. So this plus M effect here, the plus M in the first one, let us name them 1, 2, 3 and 4 for a better understanding. So in the first case, we have plus M. So plus M stabilizes the carbocation, okay, and makes the ring electron rich. Since only the first one has a plus M effect and no minus M effect, so therefore only we are making the ring electron rich. So of course electron density is the highest in 1. So 1 here has the highest electron density. Similarly, if we move from chlorine to bromine to iodine, we see that the order or the electron density in the ring goes in this order, because the minus M tends to withdraw the electron from the ring. It withdraws electron from the ring. So all these three will withdraw electron from the ring, and chlorine will withdraw the least, whereas iodine the most. So if I have to write now the order of electron density, which we are looking out for, the order of electron density, that which one has the highest number of, or is the most electron rich out of them, it is in the order that first is greater than second, is greater than third, and that is greater than fourth. So we have got an order for us that 1 is greater than second, greater than third, and greater than fourth. So this is the order of electron density. Now, moving on, we have another example here, which they all are cyclo compounds. Cyclo means they all are closed compounds. Okay, so we have the first one, cyclopropane, Then we have cyclobutane, cyclopentane, and cyclohexane. Okay. Now, we know that if there is a carbocation, if a carbocation is present, we have discussed that it has sp2 hybridization, and sp2 hybridization has an angle of 120 degrees, has a bond angle of 120 degrees. Now in the first case, if I see this angle here, it is 60 degree. The second case, it is 90 degree. In the third case, it is somewhere around 108 degrees. And in the fourth case, it is 120 degree. So the bond angles I have just told you is, so these are all cyclo compounds, and we want to find the stability of these. So we are looking out for their stability, and we have decided on the bond angles. Okay, so if the carbocation is present, and it should have an angle of 120 degrees. So in the first one, we see that this angle right here is of 60 degrees. Then we have this angle right here, which is of 90 degree. Then again we have this angle right here, which is around 108 degrees. Again, we have an angle here, which is 120 degrees. Now, what does that tell us? Now we know that carbocation is sp2 and has a bond angle of 120 degrees. So anywhere the carbocation is with an angle of 120 degrees will be the most stable. So we see that angle is least in one, that is 60 degree, and is maximum in fourth. So fourth has the highest angle, and lucky for us, the fourth angle is 120 degree for here. And sp2 is the most stable when paired with 120 degree, because ring strain, now there is something called ring strain. Ring strain is less, okay, in 4. Now why the ring strain is less? Because the bond angle is more. So ring strain is inversely proportional to bond angle. The more the bond angle, the less is the ring strain. Okay, so ring strain is less in 4 because we can say because here the angle tends towards 120 degrees. Okay, so here the angle is around 120 degrees. We are not putting a ball, it is a ballpark figure that I'm giving you. So it is tending towards 120 degrees. So the order of stability, if I write finally, the order of stability will be, since the ring strain is least in the fourth one, so the fourth will be the most stable, followed by the third, followed by the second, followed by the first. So this is the order, the final order that we wanted, and the order of stability is thus 4 is greater than 3 is greater than 2 is greater than 1. So the greater the bond angle, less is the ring strain and more is the stability. That was the example. Thank you.